Hello, we're Team 12. I'm Hunter Karen.
I'm Joanne Tang.
And I'm Nadia Ross.
So for our project, we developed an educational Rube Goldberg machine designed to teach basic physics concepts to high school students. We have, as of this moment, we have completed a system level design of the product and are prepared to move forward with production. In this video, you will find a review of design phases 1 and 2, our 3D CAD model, a review of our product architecture, a review of our industrial design, our assembly time estimation, our cost estimation, and finally our discussion of future changes to the product. So regarding project management, we did an exceptionally good job of following the Gantt chart that we had established in design phase 1. As you can see, we have completed all 3 phases of the design process. And looking back on it, in hindsight, the only changes that we would make to our project management style is that tasks 9, 10, and 11, that are designed for manufacture, our economic analysis, and our prototyping, would be considered parallel tasks rather than coupled tasks.
So a review of design phases 1 and 2. So our very first step was planning the design effort, in which the team got together and established that we wanted an educational physics product aimed for 11th and 12th grade students in physics classes. So next we identified the customer needs. We did this by interviewing 5 customers, and we identified our ideal customer as Michael Tolliver, a local teacher at a high school, who gave us suggestions on how we should improve our products. Next, we took the statements that the customers gave us and we turned them into engineering characteristics with measurable values. So for example, if a customer said they wanted a cheap product, we would put a number to that. So we'd say we aim for an ideal cost of $40. Next, we performed our first economic analysis predicting the total cost, total revenue, and total profit. So we predicted that the cost of the BRG would sell for $40 a unit, and we would have a fixed cost of $11,250. Our max profit would be, or our optimal profit would be at selling 600 units, which would bring us $54,750. Then we investigated some intellectual properties, which were some patents. We did this not only to get ideas for how to improve and add to our BRG, but also look at what limitations we have. So for example, if someone has a claim for something, then we can't add that component to our BRG. Then we went to the concept development phase, in which we went through concept generation and selection. We selected 3 concepts for the station. So station 1 concept was pendulum, station 2 was banked road, and station 3 was the elevator. So we did that by using a concept scoring table and a concept combination table, as well as a concept screening table. Then we tested the concepts using FMEA, failure modes and effects analysis, in which we identified the potential failures for each station and how we can prevent these failures, as well as how to fix them when they occur. Lastly, we had an economic proposal for investment, and we are requesting $15,924.94. This will be paid back over a period of 3 years in quarters.
So this is our 3D CAD model of our design. It should be noted that all Arduino components, string components, the pegboard, and the support rod, which will be created by the students, have not been included in this model. So over here on the left, you will see a 3D CAD model of our entire project. Ball will start over here with the elevator, obstacle 1, move through obstacle 2 right here, and then move down over here to obstacle 3, and then continue on to the exit ramp. This is our current assembly for obstacle 1, the elevator. As you can see, it consists primarily of 2 parts, the elevator shaft and the elevator platform, which can be seen inside. Our second obstacle, which is the projectile motion demonstrator, consists primarily of 4 parts. The receiving end, which is not pictured in this diagram because I wanted because we would like to show you the assembly for first part of the obstacle, and the first part of the obstacle, which consists of the ramp base, the adjustable exit ramp, if you will, and a wooden dowel so that the adjustability of the ramp can be secured. And finally, we have our third obstacle, the pendulum, which consists of three parts: the body, the dowel, and the pendulum arm.
So for product architecture, this is basically fitting the physical components to its functionality. So in product architecture, we identified 4 chunks for our product. So the first chunk is station 1, the elevator. Second chunk is station 2, the projectile motion jump. Station 3 is the chunk 3 is station 3, the pendulum. And finally, our 4th chunk is the electrical components. So we chose to design our product in chunks rather than have an integral design in order for the product to be changed easily and maintained easily. So if, say, station 2 breaks, we could easily replace that without having to take apart the entire BRG. We could just change that one part. Also, this helped us because we actually needed to change station 2 since it wasn't working out, and we were able to change the entire station 2 without really messing with the other 2 stations. This also allows for product variability. So for instance, someone wants to buy our BRG, but they want one station to be a little bit different. They want a different physics concept. They could easily add that to one station and the whole BRG would still work, and they don't need to necessarily change the entire thing. The fundamental interactions are shown through these lines. So these black lines, they go from the station to station and they show the path of the ball. And these gray lines, they show how the electrical components connect to each of the other stations.
So for our industrial design, we had to make sure our product kind of fits the needs and the desires and wants of the customer. So we used 5 categories to assess our Rube Goldberg. So we used quality of user interface, emotional appeal, ability to maintain and repair product, appropriate use of resources, and product differentiation. We use this kind of line to give our product a rating. This goes from lowest to highest, and the dot represents the rating. So for the quality of user interface, since our Rube Goldberg is very interactive, we gave it a pretty high rating, and it's easy to use as well. For emotional appeal, since our product is interactive, I think we thought it would excite the user. So although it might not be the physically most appealing, it is definitely very emotionally appealing. So we gave it a little bit of a lower rating. For the ability to maintain and repair product, we used a lot of cheap and easy to find materials. So we gave it a pretty high rating. And the appropriate use of resources, so we were able to use cheap and easy resources, and also the Arduino, which was provided to us. So we gave it a medium type rating. And for product differentiation, a lot of other Rube Goldbergs might have elevators and might have ramps and things like that, which was in our Rube Goldberg as well. So we kind of gave it a medium sort of rating. However, each Rube Goldberg, the way they operate and the way the ball runs through the product is different. So that's why it's kind of like a medium high rating. For the assembly time, we used two charts, manual insertion and manual handling chart, to predict the estimated time of assembly for the students when they get the product. There's different steps, so for example, putting the elevator together or placing the track on the pegboard to come up with a final estimation time of 10 minutes.
So this is our estimated cost. To do this, we took into consideration all the different material that we used for each component of each station. So listed here are the different components. Most of our material was just cardboard and glue, so it didn't cost us too much. So we took into consideration the cost of the material, as well as the labor cost, and then we got the total variable cost. We have overhead charges of 10% of what our total direct charges would be, and we came to the grand total of $80.25, which is our estimated cost to manufacture one of our Rube Goldberg machines. Oh, so this is toward detailed design, discussion of future changes. As you could tell, we had to make some changes after our concept selection. So what our actual product was, we didn't use the same station that we had initially chosen. And this was due to the fact that we didn't really test the entire product as a whole. We just tested the stations individually until the final design, the final assembly. So that's why we didn't figure out that the stations couldn't really work together as we had planned, and that's why we made last minute changes. So in the future, we would like to test the system as a whole, not necessarily physically, but we could create analytical models using CAD, and we could perform finite element analysis, which is something that we hope to learn in our future engineering analysis classes. So some of the questions I have for these classes are, how can these computerized analysis such as FEA accurately predict the failures? So if the analysis says it won't fail, how likely is it that when we actually do it, the station will fail? Also, what types of analysis will take into account the materials used? So for example, when we were testing, we used one type of string for our elevator, but then when we changed out the string for our actual assembly, that didn't work, and that caused the string to be all tangled up. So we think that if we had investigated this ahead of time, we could have prevented this problem. Lastly, even though we had our product reviewed by professors as well as our peers in our engineering classes, we never really had the product reviewed by the actual customers for our product, which is 11th and 12th graders. So we feel that in the future, before we put this out on the market, it'll be important to have these students review the product to ensure that this is the correct difficulty for them, that they enjoy it, and also that they're learning from it.
And for DP3, Design Phase 3, which we are discussing today, we presented and tested the final Rube Goldberg design. So we were on track for all of our time sets. But as Hunter mentioned earlier, it would have been better for three of the tasks to be parallel and not coupled. We also discussed DP1 and DP2, which Joanne discussed and I just kind of went over. We also presented to you the final CAD models for our design and kind of how we had to change Station 2 from a banked road to more of a jump between two ramps. For our product architecture, we had four different chunks. We had one for the elevator, basically one for each station, one for the elevator, one for the ramps, and one for the pendulum, and also one for the electrical components. And we chose this type of design so we could be able to change each station without having to change all of the stations. And for the industrial design, so we had pretty good ratings for each of our categories, whether it be product variability or things like that. So yeah, and for assembly time, we came up with an assembly time for about 10 minutes using the two manual handling and manual insertion charts. And for cost estimation, through the materials that we used, we came up with a cost estimation of manufacturing each product of about to be about $80. And for future changes, we decided that to kind of make our product better where we don't have to change stations around and things like that. We should have tested the entire Rube Goldberg together instead of testing each station individually. And so for other future changes, we could test using kind of CAD models and finite element analysis with the materials that we used. So thank you guys for listening to us and being with us for DP1, DP2, and DP3. We believe we created a very successful final product. Thank you, and I hope you enjoyed our presentation.